Good morning, everyone. Thanks for coming. And this is my first time in Moscow, so pretty awesome feels. So my name is Ankur Anand. I work for SAP Lab India, and if as my talk says, it's an illustrative exploration of Go memory allocator. I will try to visually dissect all the data structures and all the nitty-gritties of Go memory allocator in the limited time whatever I have. So let's get started. Also, if you have any questions, do feel free to ask me on my Twitter handle. Even after the talk, I would be happy to answer all your queries. So before we go into Go memory allocator, it's necessary to have the basic fundamentals at our site so that we all are on the same page. Let's see, this is the RAM, 1-bit RAM on the top, and means RAM is composed of, just basic RAM composed of a capacitor which holds the charge. You send electric current on the address line. If it holds the charge, it gives you 0. It gives you 1s. If it does not hold the charge, it gives you 1s. So this is what RAM is basically composed of. But are we using this 1-bit? No. This is what our RAM looks like, right? We have the CPU that places the address on the address bus. So depending upon the address bus size, we have the pointer size. So if we have 32-bit address over here, it's 32-bit. So we will have pointer size of 4 byte. If the address bit is 64-bit, we will have the pointer size of 8 byte. So on the lowest side, you can see we have on this, we have on the here, we have the 32-bit of byte address, and on the top, we have 32-bit of byte addressable ones. That means it's the highest address. This is just for the illustrative representations. Actual working is quite complex. But since this RAM is limited, and we have more than one program running on any given time on our operating system, what happens? We divide this, we have a necessary separation before this. We call this virtual address. And it's the piece inside the operating system, that is MMU, that is responsible for translating this logical address to the physical address. This we all are familiar with. We have a physical virtual address space, we have a code segment, we have a data segment, we have a heap over here, and then we have a stack that grows downward, heap that grows upward. As you can see, there is one point inside the heap, that is the break point. So this is what signifies what is the current heap size in your program. So since this, let's suppose we have a 4-thread running. All wants to increase the heap size. That means it has to increase this breakpoint. So we suffer from one problem. If we do not do locking over here, there might be memory corruption because you don't know which thread is going to increase this breakpoint. So to prevent that, we have to have locking. Now, in real-world scenarios, we have various threads running, and this locking, since this locking is at the application state, we have this issue of lock contention, which is very costly affair. Second is, also since this breakpoint, increasing the breakpoint means we have to map this to physical address, so operating system has to know this when this breakpoint has been increased. That means involving a system call. So we will try to figure it out in our memory allocator, how we can amortize this breakpoint increment and system call. This is a typical life cycle of your memory page. You have an application that have allocator. Also you have a virtual memory space. So you have a heap over there. If that heap is already allocated, you do a load and store operation to access this memory location. And if you need to increase the heap size, you do a system break call. And if that page is not found, it will generate a page fault, and MMU will do all the necessary translation. Okay, now we have the basic idea about means what happens at the operating system. Let's focus on the application side. Here we have a chunk of memory. In the first P1, we allocate 4 bytes. In the P2, we allocate 5 bytes. In the P3, we allocated 6 bytes. Now we have 2 bytes left. In the fourth operation, we freed the second operation. That means we freed the 5 bytes. But in the fifth operation, we want to allocate 6 more bytes over here. What would happen now? Because these memory are not continuous, we cannot allocate. Even though we have 7 bytes available over here, there is no allocation happening. And this is the external fragmentation. So whenever we are writing any such allocator, we have to deal with 2 things fundamentally. One is this fragmentation issue that we just suffered. Second is how do we decentralize the locking at the application state. Before that, so we know that this is the Go scheduler overview, right? All the Go routines runs on the logical process. And it's the job of the runtime to map those Go routines to the native M thread. So M is your system machine thread, G is the Go routine, and P is the logical process. So if you do not twinkle with the Go setting, if you have 4 core, that means there will be 4 logical processes running for inside the runtime. And since all these Go routine, only one Go routine can run, one Go routine can run at P at any given time. So how do we deal with this? Also, the virtual memory space is divided into different pages because logical address space, let's suppose for 32-bit, for 32 address line, we have almost 4 GB of logical space for each program. It's quite tough to deal with all those bits and bytes individually because you have to, operating system also needs to maintain all those data structure where it needs to map this logical address to physical address space. So it's deal in the term of pages. Most operating system that Linux and deals within the size of 4 kilobytes. But Go manages this page size in the term of 8 kilobytes. So first thing, how do we efficiently satisfy the allocation of given size but avoid fragmentation? As we have seen, we have a page. What we do? We divide the page into given class sizes. What it means? Let's suppose we have a 8 kilobytes of page. What we do? We divide it into different sizes. 8 bytes, 16 bytes, 32 bytes, 48 bytes, up to 32 kilobytes. So if you are looking for an object that corresponds to 7 bytes, it will be, what is the number we are looking for? We are looking for the page size which has been divided to 8 bytes of around here. Why these numbers are not to the power of n? These numbers are based on the tcmalloc configuration, and it has been the tcmalloc has been written by the Google, and Go memory allocator directly inherits so many components from tcmalloc. And also these has been designed so that the total memory after the page chopping of these pages gives you at max 12.5% of wastage of memory. So this is it. So how does this mix fragment solve the issue with fragmentation and also fast allocation? So we have seen we have different span classes. So we have the pages, and the number of pages in each span is also done so that the total wastage is again 12.5%. So we have a span add class for each M span structure. We have a start address. We have number of pages. These are the most common used structures inside that. So on the bottom, you can see we have a runs of pages divided into certain blocks. So let's suppose for this, we are dividing it into 32 bytes. So we have 8 kilobytes of pages divided into 32 bytes. So we get total of around 256 such blocks. If an app, and also it maintains which block is free, which block is occupied. That means when looking for the page of object of given size from this particular structure, all we need to do is find the first free block. That means we have a fast search for allocation. So this is the size. If you need any object to allocate, it will first calculate the size of memory required by the object, then calculate the required size class, and then it based on the mapping, it will give you that span. We will also look into the third point, which is really important, calculate the span size based on the size class, and whether the object contains pointer. This is really important for garbage collection point of view. This is what helps garbage collection becoming so fast. Okay. Since we have, this is the so we have a MCAS. What it does, it pre-allocates up to 32 kilobytes of memory divided into M span of each classes and keep it with itself. What this does, because only one Go routine can run on logical processor P. So if any Go routine that is trying to allocate memory up to 32 kilobytes can directly get from the MCAS. Also for each MCAS, if you see, we have for each classes, we have a two structure. We have a no scan, we have a scan. What it means in the real world, if the object does not contain pointer, it will go to no scan class, and if it contains a pointer, it will go to the scan class. So during the garbage collection, if you have tons of thousands of objects, the garbage collection only needs to find this no scan, so scan class object, and will only scan these classes for the pointer check. That if this is contain pointer, it will just diverge towards the next pointers, whatever it points to. So with this structure MCAS, if we have MCAS per P, we have avoided the locking in the common scenario. Plus, since this object is already precast to the logical P, we are not making any system call at that point of time. That means faster allocation. How we can utilize this knowledge of no scan and scan in the real world? Here is the example. So every optimization has certain drawbacks. So optimize your code only if you know this is the problem. Benchmark it, profile it, then optimize it. Here is my two structures. On the left side, you can see I have a pointer at the second element. On the right side, I have a pointer at the first element. What I mean by limit your pointers over here. Why this helps in the garbage collection. Let's suppose on the right hand side, if and Go garbage collection needs to find out if this structure contains pointer or not, it has to only scan one element. Go also maintains metadata for each object that it has allocated, where it needs to stop further scanning. In the left hand side, it has to scan all the two objects to find out, okay, where exactly is the pointer. So in real world, if you have tens of elements over there, thousands of elements over there, and if your pointer contains at the last element, it has to scan all those 10 elements. So you can see all the 10 elements before the pointer carries no value for the garbage collection. But for you, it might matter or does not matter. It depends upon your application. But from the garbage collection point of view, it will increase your stop the world sometime. Also, allocate memory in batches. It prevents you from being preempted, because each memory allocation preempts the Go routine from running at that point of time. There are lots of pattern of evolving around sync.pool where it tries to recycle objects. So you might have seen lots of framework coming up where they say we will use pool of Go routines so that we do not allocate in the fast path, or buffer pool. There are pattern coming up for using the sync.pool. It's also Go team is also evolving sync.pool so that it can multiple Go routine can access that structure which you have pulled inside sync.pool in a lock-free way. At some point of time, your MCAS will get filled. What happens? So Go also has mCentral. It's one more level of CAS. So this CAS, what it does, for each size classes, we have around 67 size classes. For each size classes, it again maintains two lists. One is you can see non-empty list, one is the empty list. And it involves lock. But if you carefully see over here, we have this span class. And the lock is involved only at the span class. So this is very carefully designed so that if you have a two Go routine asking for memory and the MCAS does not have this memory available at them, it will go consult mCentral. But since these two Go routines are asking for different size classes, it can be served parallelly. So this is quite a distinction over here, that this CAS can serve if you have multiple Go routine if it's not asking for the same size class. Also, this non-empty means the object based on the certain calculation, if this object has been garbage collected and it has been returned. Empty means there is no free object inside. Yes, the naming conflict, but that's how, I don't know the reasoning behind naming such way, but this is the way it operates. So here is the hip for me. Then gist of it. So we have this mCentral. We have already seen the mCentral is the data structure that is contained inside the mHip. On the right side, we have more data structure. It's a sorted tree based on the number of pages. It's scabby and free. Also, we have arenas. This contains hip arenas. We will look into arenas. For now, we have already seen mCentral. We will look into scabby and free object. So any object, if you have and also we have a lock, central lock over here. So let's suppose your application is asking for any object that is greater than the 32 kilobytes. It will be directly allocated from this mHip structure. And since this involves locking, so your entire app, only one Go routine can access this structure at a time. That means this is critical for if you are having large object and this becomes critical path for your application, you might try to use sync.pool. Why? Because you already have the sync.pool, already object is allocated in the sync.pool. You don't need to lock the entire application for other Go routines. We'll look into the hip arenas now. Why it's essential means arenas is constituted of hip arena and how this helps with the memory allocation. Here is the virtual memory layout of inside the Go. So we have a span, we have a bitmap, we have arenas, we have hip arenas. So arenas is constituted by different hip arenas. Each hip arena is of size 64 MB on the 64-bit Linux. On other operating system like Windows 32-bit, it's 4 MB, but that subject is subjective to change. So right now it's 64 MB. Take this number with grain of salt because earlier it was around 512 GB altogether in single Go. So these numbers can change in further Go version. So these numbers are based on Go 12.5. So we have a hip arena, we have a bitmap. So bitmap is what helps you during the garbage collection. As we have already seen that these numbers will help when we are as a garbage collection want to see when to stop this object from further scanning to find out if this object contains pointer or not. Again, the same thing. This object will stop for the left-hand side. The bitmap will point, okay, I have to stop at the second element over here. In the right-hand side, the bitmap will contain the metadata, where it will see that I have to stop at the first element itself. So this helps in during the garbage collection. So bitmap is basically more of your metadata container. Now, heap arena is actually where your allocation works, and arena is made up of different such left-hand side structures. So arena is composed of different heap arenas, and this heap arena can be continuous, or this can further drill down, means number of operation number of object you have allocated, this heap arena number can change. Let's look what is the size. We can also verify the size of heap arena, initial heap arena. I have a simple program that does nothing. It's simple for loop running forever. If we look into the memory of this, you can see for virtual size VSZ on the Linux, we have around 100 MB, but the actual physical size is 696 KB. Why the difference? As this is the process stack. If we look further down towards this, we can see that we have one memory allocation of SMAP 65 MB, one is 35 MB. So this 64 MB is what your initial heap arena. So because my initial when I started Go, that for simple for loop, my Go did not do any allocation. I didn't need any allocation, but Go took this told the operating system I need 64 MB for myself. Why? Because this involves system call, and this amortized your further, means until and unless I have filled up those 64 MB, I am not talking to the operating system, because operating system has already given me those 64 MB of memory. And this 35 MB is something where your bitmap resides. All the metadata about the object resides. So how does this helps? If you go into, there is a Twitch TV, they have really nice blog, because also during the GC, if you look into the GC, there is one thing, how GC memory pace. So if you have when does GC runs, right? So there is something dynamic pacer inside the Go runtime. What it does basically is, if you have, it will always try to clean the GC when, let's suppose I have a 64 MB of RAM. Next allocation will happen at certain point, and when will GC try to free up the previous allocated object? It will try when your current heap size doubles. So this is a real world scenario where Twitch TV tried to, means they worked upon, they initially allocated around 10 GB of RAM, so that next garbage collection will take place only at 20 GB of heap size, so that they don't have any garbage collection during the live running code. And this helped them pretty much. You can see in the blog, they have detailed it out, how it reduced their latency and all this with the help of this memory blast. So here is the allocating flow summary. So since Go uses hierarchical access to memory and also accesses by size, and according to size, whether it's a pointer, there are three kind of allocations that happens. If you have a small size object, that means if it's less than 32 kilobytes, you will allocate directly from the MCAS. What it gives you? It gives you no fragmentation at all, plus it's a lock free. So multiple Go root. So if your object is less than 32 kilobytes, you are almost certain that you will have fast allocation. Also, there is one allocator with tiny size. If the object is 16 bytes and it contains no pointer, it will be allocated in the tiny allocator. Why? This is to reduce further fragmentation, because if we have how does memory actually allocate? It has to be boundary, at the word boundary. That means if you are allocating around 5 bytes, it won't allocate 5 bytes for you. It will allocate that entire object needs to 8 bytes, because while accessing, this has to be aligned with the word boundary or the address space. So this tiny size Go helps with over here. It actually allocate 5 bytes only, and rest 3 byte it will allocate even tiny object. So Go helps over here, and also if you have a large size object that is greater than the 32 kilobytes, it will be directly allocated on the global heap. So that means your application, only one Go routine can access this 32 kilobytes of, if it needs to allocate memory on the global heap. So here is the in general summary of entire overview of the Go runtime allocation. You have a span at the top level and that's for each P, you have a total of 134 span for each class size. Each class size is like 0, 8, 16 like that. And for each span classes, you have also another level of cache that is M central, and these M central resides inside the M heap, which contain free list and scanv, and these heaps are basically constructed from arenas, which constitute of your original page of 8 kilobytes, and these arenas you get from the operating system. So with that, thank you. Any question?
Okay. Do you have a question to Ankur? I'm pretty sure you don't, but if you need a translation, I can do it for you. В смысле, если вы боитесь задать вопрос на английском языке, я готов его для вас перевести. Так. It was tough. Yeah.
Hi.
Hi.
Yeah. My name is Awan. Thank you so much for the presentation. It was perfect. But I have one small question regarding this example with performance improvement,
Yes.
according to like how we can reduce the amount of sequence scan.
Yes.
Yeah, why not to store this information regarding does the particular struct the pointer reference or not? We can store this information inside like some kind of metadata to not to scan the structure every time we want to allocate the new instance of this structure. I mean, why not to just store this information in compile time somewhere, and then we don't need to scan the whole structure, whole attributes to decide do we need to put the instance of this structure to scan or no scan mspan.
So what you are basically asking, why not to store this metadata inside the structure itself?
Yes, yes, yes.
I think Java pretty much does the same thing. There is also issue with that when you store metadata inside the structure also, your structure size is different, right? So for storing metadata, over here, you need certain field values to be injected at the compile time. That means whatever heap profile, if you are doing allocation and you are thinking that, let's suppose I have a I have a structure that contains 2 integers. So I'm pretty much sure on my 64-bit, it will be 128 bytes, right? But if I contain metadata, I'm not sure what is the size of this object, because this can change behind the scene for me.
Yeah, that's right, but I'm talking about that we don't need to store this metadata for each instance of the structure, but we can store it only once for each structure, and not inside this structure, but in some kind of other data structure. Like, okay, we have 3 declared structures, let's say sample 1, sample 2, sample 3. Okay. We have no instances. I mean, during the compile time, we cannot find the allocation, for example. Okay. But for each structure, we additionally store the fact that does this structure contain a pointer or not.
Okay, so if we store this at the compile time, how will garbage collection know which object is live or not?
Excuse me, can you
okay, so if this structure means for you, let's suppose I have a 3 structure and I store this at the compile time. The garbage collection has to exactly know how many live instance of this structure is there inside my program. that information I cannot get at the compile time.
Yeah, sure, but
I'm sorry, probably I have an answer to your question.
okay.
If you store this information in one area of memory and you store your structure in another area of memory, you will have to drop your cache of your CPU, load the first part of the memory, then drop it again and load the second one. And this is the most expensive operation in our world.
Okay. Thank you. Thank you so much.
If that answers your question.
Yeah, I'm sorry, I
Thank
didn't.
you. Yeah, perfectly fine.
Okay.
Thank you again.
Do we have another question? I would tell you we have a prize for the best question. So for the moment we have just one question, and it will become a best if you will not ask anyone other. No questions? Okay.
Okay.
Hello, my name is Alex. My question is, can we turn off memory management and make it more manually with some kind of magic and syscalls?
Yes, there is a nice talk from Uber, company from Uber, where they exactly did this. They turned off the GC and they used unsafe pointers and wrote their own, code to not use GC from the Go code at all. So if you are comfortable with unsafe and you know what you are doing, you are most welcome.
Thank you.
Any other questions? That's it? Really? Okay. So, Ankur, you have to decide which question was the best.
Okay.
And we will provide a prize.
I have no idea how do you decide which question is the best. Maybe you have answered, so you have listened both the question and you have answered, so you might be the better judge of.
Of course, the best question is what I ever answered. Always.
Yes.
Okay. I spent 3 years teaching in the children in school. So the best question is I know the answer. Yeah, okay. So thank you very much.
Thank you.
We have a small present for you. This, oh, can you do it? Okay, this small matryoshka gopher.
Thank you. It looks so nice.
It is. Okay, thank you very much.
Thank you.